So in this video, we're going to talk about the squeeze theorem, sometimes called the sandwich theorem. So let f, g, and h be three functions on some interval containing a number c, so that g of x is sandwiched, it's squeezed between f and h, okay? Now, if this is true, and we know that the limit as x approaches c of f of x is equal to the limit as x approaches c of h of x, and that number is equal to L, okay? Then that means g of x, which is stuck in between those two, has to also limit to L. That's the idea of the squeeze theorem. In a way, f of x and h of x are squeezing g of x at c. So maybe this can be illustrated a little bit better in a picture. Now, in this first scenario, we're going to show you why we need to not only have this to be true, but also this second part here, okay? And so to do this, we are going to have two functions, f and g, whose limit is not equal to each other, okay? Whereas here they are equal to each other. We're going to do a scenario where that's not true, and I'm going to show you why it has to be true for it to work. If it's not true, say you have some h of x that's bigger, right? So maybe it's like 5 up there, and then some f of x that's lower, maybe that's like 1 down there, right? So those limits clearly at c, those are not equal to each other, okay? Then what does that tell us about g of x at c? Well, that doesn't tell us anything about it. Even though that g of x is between these two, all it tells us is the limit is somewhere in this range here. That's all it tells us. It doesn't tell us exactly what it's equal to. So let's show the scenario where not only is g sandwiched between the two functions, but the limits of the top and the bottom are equal to each other. Okay, so we have some h of x coming down here and some f of x pinching up here. So what does that do? That squeezes, hence the squeeze theorem, it squeezes our g of x so that it has no choice but to be equal to the same limit as the h and f function at that point, okay? So that's the idea of the squeeze theorem, or sometimes known as the sandwich theorem, right? You get your meat and your bread, right? The bread sandwiches the meat in the middle, it sticks it there. Therefore, it has to be the same value, okay? That's the idea of the squeeze theorem. Very powerful, allows us to prove some very difficult limits. For one, so this is the scenario where the h of x limits to the same thing as the f of x limits to at c, okay? So the next one is the limit as x goes to 0 of sine x over x. So if I plug in 0, I get sine of 0 over 0, which happens to be 0 over 0. That's indeterminate. The problem here is there are no factors in common between sine x and x, right? So I can't just factor it. So I've got to be able to use the squeeze theorem, since, that's what I just came up with, right? So we're going to use the squeeze theorem to prove that this limit, this very special limit that you need to memorize, is equal to 1. Okay, so it's something you need to memorize. So how do we do this? All right, so first I'm going to take a unit circle. So let's think about the unit circle for a second. On the unit circle, every point on the unit circle is a distance of 1 from the origin, right? Okay, now what else do I know about the unit circle? Every point on the unit circle is defined by cosine theta comma sine theta, okay? So any point on the circle is defined by that. So what I'm going to do is I'm going to set up 3 triangles, and we're going to show through area that this inequality holds, okay? So here, my first triangle, right, is going to be this big triangle right here. Now, how do I find the area of that big triangle? Well, I need to use similar triangles to do this. So first, I'm going to do this little triangle in here. So that little triangle in there, okay, if this is the xy value, all right, then that means that this side is cosine theta, and then this side is sine theta. Okay, so that's what this side is right here. Now, what I really want to know is this big triangle right here, right? Well, what else do I know? I know that this is a unit circle, so this side of that triangle is 1, but I don't know what that side is, so I'm just going to call it x. So I'm going to use properties of similar triangles to figure out what x is. And so if I take x divided by 1, this is equal to sine theta divided by cosine theta. Okay? Idea of similar triangles. So what does that mean? X is equal to sine over cosine is tangent theta. Hence this point up here is 1 comma tangent theta. Okay, that's where that came from. So how do I find the area of a triangle? I do base times height divided by 2. So tan times 1 is tan, divided by 2 is the tangent of 2. So that's the area of that biggest triangle. Now, to get the area of a sector, you know from pre-calculus, this is 1/2, 1/2 of theta r squared, right? Okay, so to do this, what do we know? R on the unit circle is equal to 1, so this becomes 1/2 of theta. So that's theta over 2, okay? And then here, this last triangle here, remember to find the area of a triangle, all you need is the base times the height. The base here for the unit circle is 1, okay? And clearly this is less than that little hump there, which means that it's a smaller area, right? And so base times height, so sine theta times 1, and then divide by 2 gets you sine theta over 2. So how is this helpful for us? Well, what we've got here, it's a lot to erase, right? I'm trying to erase this real quick. Okay. So what we have here is tangent theta over 2 greater than or equal to sine theta over 2, okay? And so what I can do is I can multiply everything by 2 over the sine of theta. Well, guess what, guys? The tangent of theta is sine theta over cosine theta, right? Okay. So if I multiply everything by 2 over sine theta, I'm going to get 1 over cosine theta greater than or equal to 1. Okay? Now, I also have this theta over 2 in the middle here. So I'm going to move this over a little bit. And I'm going to have theta over sine theta. And then my 1 here. Okay? Because when you multiply theta over 2 by 2 over sine theta, you get this right here. Okay? Now, this assumes that theta is in the first quadrant, okay, between 0 and pi over 2. Because if if you didn't have it that way, then you might start dealing with negatives and then your inequalities would turn around. But you can still show the same thing is true for negative theta values, okay? We're only concerned about thetas near 0 since we're taking the limit as x goes to 0, okay? So when I do the reciprocal of 1 is 1, okay? If I do the reciprocal, the inequalities flip. And so the reciprocal here is sine theta over theta. And the reciprocal here is just cosine theta. Okay? Now, what do I know? Well, the squeeze theorem says what? I've got functions that are bigger and smaller. And then if I can take the limit of those bigger and smaller functions and they equal a number, and that's the same limit, then I know the one in the middle has to be the same. So I need to take the limit of cosine. So if I take the limit of cosine, what do I get? Limit as theta goes to 0 of cosine is 1. The limit as theta goes to 0 of 1 is 1. So what does that tell me? That forces this to limit to 1 as well. Okay, so that's the idea. See how long it takes me to get back to where I was. Not efficient at all, but that's the best I can do right now with a broken finger. Okay, so I think this is just walking through what I was just talking about. So we find that since cosine and 1 are greater and lower than the sine x over x, but whenever I take the limit as x goes to 0 of both of those functions and I get that it's equal to that number 1, this is what shows me. So when I ask you for a squeeze theorem, to use the squeeze theorem to prove it, I'm looking for an inequality that sets this up, and then I'm looking for limits of these two extremes here, and they need to be equal to each other. And then I can say by the squeeze theorem that this limit is equal to 1. Okay, so that's what I'm looking for, that setup right there when you're going to solve these types of problems. So there's special limits. So these limits you can memorize, okay? So these first two for sure. All right, I'm not too concerned about these. We'll talk about those later in the class. Your textbook throws them in now, so you might be expected to know what they are. So you don't need any justification when doing these. We proved this first one here. I'm not asking you to prove the other ones. So you just need to know what they equal. Okay? So what do we know about the first one? Well, since this sine x over x, I'm dividing two functions and it equals 1 and the limit as x goes to 0. So what can you say? You can say that sine x and x are relatively the same size as x approaches 0. Relatively the same size because the ratio is equal to 1. If I take a number 5 and I divide it by 5, that equals 1, right? So 5 and 5 are relatively the same size. If I take a number 5 and divide it by 4.9, I get something close to 1. That means that they're relatively the same size, right? Relatively. Now, the second one here, I have a function cosine x minus 1 divided by x. Now, this ratio heads to 0 as x goes. So what does that mean? That means that the numerator, if a fraction goes to 0, that means that the numerator is going to 0, right? So the numerator is heading towards 0 faster than x is heading towards 0. So cosine x minus 1 is heading towards 0 quicker than a linear fashion of x. Okay? So let's try to calculate the limit as x goes to 0 of sine 4x over 4. Now, what's the difference here? Inside my argument of sine, I have a 4 here. That's the big difference. Now, the way this works is it's the sine of something over the sign of that, or the x of that same something, and you're taking the limit as x goes to that thing right there. So all those x's match. However, here and here match, but you can see that this does not match that right there, does it? So we need to make it match. So how are we going to make it match? I'm just going to put it in, okay? How do I put it in? If I have a 4x here, I want a 4x down here. But if I put a 4 in the denominator, I also have to put a 4 in the numerator. That's the idea there. You're putting a clever 1 in the top and the bottom. It's 4 over 4 you're putting in there. And now that I have this matching 4x and that 4x there, what I can do is I can pull that constant out front, okay? And so when I pull that constant out front, that 4 comes out front, and then I know what this limit is. Sine of 4x over 4x, that's equal to 1, okay? That's where that's coming from right there. All right? Next up, this is in general. Whatever my argument is in here, if it's blop, then I make sure I have the same blop in the denominator, and no matter what, that's always going to equal to 1. You got to make this denominator match what's in the argument of the sign here. That's all you're doing is you're algebraically manipulating it. You see, what did I need here for this x to make it match? I needed to put a 4 in there. But if I put a 4 in the denominator, I also had to put the 4 in the numerator. That's the idea. Okay? So if you got that down, then all those types of problems are going to be pretty easy. Okay? What about this one here? Limit as x goes to 0 of cosine squared x minus 1 over x plus x cosine x. Well, in the denominator, I see that I can factor it. I can pull an x out of both of those. In the numerator, it looks like a difference of squares. So like kind of you can think of it like an x squared minus 1, and then you take x minus 1 times x plus 1, right? Where x is cosine. And so the numerator factors to cosine x minus 1 times cosine x plus 1. The denominator, we GCF to x out of the denominator here. And so what do I get? I cancel my cosine x plus 1 factors, and I have left cosine x minus 1 over x. The limit is x goes to 0. Guess what? This is a special one right here. That limit is equal to 0. Okay? So another one that you need to have memorized. Okay? So that limit there is 0. Now this one here, this one is an example so you can see how to use a squeeze theorem, okay? If I try to plug in 0 here, I get 0 times the cosine of 1 over 0, which is undefined. This falls apart. I can't do that. Okay, so we've got ourselves a situation here. Now, one thing that's going to be helpful for you when you're dealing with trig, anything trig, you think about sines and cosine. What do you know about the sine and cosine graph? No matter what, it's always bigger than -1 and always less than 1. Okay, doesn't matter what's inside the argument of the cosine. Doesn't matter what that is. It's always stuck between -1 and 1. This is how we set up our squeeze theorem. All right, we get something that's bigger, something that's smaller. Now that doesn't look exactly like what I want. What am I missing? I'm missing this x squared. So what am I going to do? I'm going to add an x squared in all 3 pieces. So let's add it. So I multiplied everything through by x squared. Okay, now what do? I have the inequality set up. I need to take limits on the extremes, and then hopefully they match, and so that means the middle has to be the same. If I take the limit as x goes to 0 of -x squared, what does that get me? That gets me 0. If I take the limit as x goes to 0 of x squared, that gets me 0. So I got 0 and I have 0. So what does that tell me about the limit of the inside here? By the squeeze theorem, that tells me that the limit as x goes to 0 of x squared times the cosine of 1 over x squared is equal to 0. So you have to show me this, you have to show me this, and then you can say this is true. That's how you use the squeeze theorem, my friends. It's an if-then statement. If these things are true, meaning if this is true and this is true, then by the squeeze theorem, this has got to be true. Okay? All right, guys, good luck as you work through these problems. You know what? I just want to make sure we understand this one, okay? Because I didn't feel too good about that example. Let's do another one. Let's do the sine of 2x over 3x, okay? So look, what's going on here, all right? It doesn't quite look like sine x over x, okay? But it's close, right? One thing about it is it's a reciprocal going on here, so I need to flip that. Well, how can I flip this? Algebraically, I need to manipulate this right here. So I want it to flip, so what I'm going to do is I'm going to write it as a fraction of sine 2x over 3x. Okay, so you kind of see what's going on here. So I have a fraction on a fraction, and if you do the keep, change, flip rule, then this will get you back to what you had started with. Okay, so that's a little trick for you to get it written. Now look, I got a 2x there, but I have a 3x down there. How am I going to fix this? Well, what I'm going to do is I'm going to factor this 3 out because that's just kind of annoying me. Okay, so I have 1 over sine of 2x over x, and I have this 1/3 thing going out over here. Okay, I pulled that 3 out to over here. So now what do I want? I want this to match this. How do I make it match it? I put a 2 here. But if I put a 2 in the denominator, I need to put a 2 in the numerator. Okay? So now what's going on here? I have 1 over, now this 2 here, that's a 2/3, right? And then I have a sine 2x over 2x. Now I know that this limit, whenever I bring my limit in as x goes to 0, this thing is going to go to 1, okay? So really, what do I have? I have 1 over 2/3 times 1. Now fraction, keep, change, flip. I keep 1 the same, and I change from division to multiplication, and I flip the denominator. So my answer is the reciprocal of 2/3, which is 3/2, okay? So that's like the most complicated thing you're going to run into right there, okay? So hopefully that's going to help you a little bit.